Hey everyone, welcome back to Abstract Algebra 1. This will be part B of lecture 5. So where we left off, we had just defined what a subgroup was, and we had looked at two methods, two theorems, two subgroup test rules that would allow us to determine whether a particular subset of a group happened to be a subgroup. Right, and so what we're going to do is we're going to look at one more subgroup test. And when you're dealing with finite groups, this is oftentimes the most straightforward. So when dealing with finite groups in particular, this may be the most straightforward method for showing that H in G is a subgroup. Okay, right, so the theorem says, let H be a non-empty finite subset of a group G. Let H be a finite, non-empty subset of a group G. Okay. Then H is a subgroup of G. It's a subgroup of G if H is closed, if it's closed under the operation of G. Okay, so this is a good one, right? So basically, if we know that the group G is finite, has a finite order, then all we really have to do is show that H is closed, that there's closure, and that will automatically imply that H is a subgroup. Okay, so this is usually the fastest and simplest way to prove that a subset is a subgroup if the subset happens to be finite. Or sorry, if the group happens to be finite. Okay. All right, so let's prove this one. This one will be a little bit more challenging, but I think we can do it. Okay, so to prove this to prove this test, we really need only show that the inverse of A is in H whenever A is in H. And if we can do that, then we'll be able to fall back on the two-step test from the previous theorem. So we're daisy chaining all of these theorems together. So to prove this, we really only need to show that A inverse is in H whenever A is in H. Okay, and then given that, we can apply the two-step test. The two-step test from the previous theorem. Okay. Okay, and so let me. Okay. All right, and so let's go ahead and try to show that A in H implies that the inverse is in H. Okay, so the way let's consider two cases. So the first case is really straightforward, right? So the first case is when A is equal to the identity. So if we let A equal E, then that's going to imply that A inverse is equal to E, which is equal to A, and we're done. Okay, so that's case one. So going forward, we'll assume that whatever A we're talking about is not the identity. Okay. So now we'll be assuming that A is not equal to the identity. All right. And what we're going to do to kind of build this up is we're going to start with a sequence that we know is in H. Okay, so consider the sequence a to the first, a squared, a cubed, dot, dot, dot. So A is in H, and so A times itself is in H, and A times itself is in H, right? These are all in H since H is closed. Okay. Okay. And since H is finite, right, here's where the finite group piece comes in. Since the order of H is less than infinity, right? And this is obviously an infinite sequence. So because the order of the group is less than infinity, that this sequence must necessarily start to repeat itself, right? It must start to repeat itself at some point. So another way to say it would be that since H is finite, not all of the elements in this sequence are distinct. That'd be another way to say it. Okay, so what does that mean? Well, so sum a to the I power is equal to sum a to the j power. And without loss of generality, we're going to let I be greater than j. It doesn't matter which direction you choose that. So it's one or the other, right? So without loss of generality. Okay, then we can do a little bit of arithmetic here. Right, then it follows. So if AI equals a to the j, then AI divided by a to the j is equal to e, which implies that a to the I power minus the j power is equal to e. Okay. All right. Let me switch pages here. So a to the I minus j power is equal to e. Let me put that last sequence. Let me rewrite it so it's on the page in front of us. So we had a to the I equals a to the j. We know that's true because the group has finite order, and so some elements in the sequence a1, a to the first power, a squared, a cubed, a to the fourth, dot, dot, dot. Some elements in that sequence must be equal to one another, otherwise the group would be infinite, right? So that implies that there's some ai equal to aj, right? And from that, we can say that a to the I over a to the j is e, and therefore a to the I minus j is equal to e. Okay. Now, we assume that a is not equal to e. By assumption, remember that a is assumed to not be equal to e. And so what does that mean? Well, it means in particular that I is not equal to j. I think that part of it's straightforward, but it actually implies that I minus j is greater than 1. Okay, because if I minus j is, remember I is assumed to be greater than j, so obviously I minus j is greater than or equal to 1, right? They're not the same, but we're saying something stronger. We're saying that I minus j must be greater than 1, and that is going to follow from the fact that a is not equal to e, right? Now we can say this because if I minus j equals 1, we'll end up with a contradiction. You know, I could let's do a specific example, but all examples would follow. So if I let I equal 2 and j equals 1, then that means that a squared is equal to a, which means that a times a is equal to a, right? Which implies that a is e. Okay, this can only really happen if a is the identity. Okay, so then, that's kind of an aside. I mean, it's important, right? This part is important to make sure you understand why that's the case, but what's really important here is that I minus j be greater than 1. And so that basically means that in the sequence a to the first, a squared, a cubed, dot, 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 the ai and aj's that are equal to one another are not sequential. They're not next door to each other. Okay. All right, so what do we have then? We have that a to the I minus j power is equal to e. Okay, let's just do a little bit of arithmetic on this. Let's multiply and divide by a simultaneously. So a over a times a to the I times a to the I minus j is equal to a over a times e. Okay, and so this is really over on the right, on the left hand side here we have a times a to the I minus j over a. That's equal to a times a to the I minus j minus 1. So this guy here just comes up top, minus 1, right? And that's equal to a times e over a, which is just equal to e. All right, so the key here are these two. So what we're saying here is that a times this other guy, a to the I minus j minus 1, is equal to e. Okay, and what that implies is that a to the I minus j minus 1 is equal to a inverse. Okay, so we found the inverse of a. It's this a to the I minus j minus 1, whatever I and j happen to be. So the question is, we know that a to the I minus j minus 1 must be the inverse of a. How do we know that a to the I minus j minus 1 is in H? Right, so how do we know that a to the I minus j minus 1 is in H? Well, a to the I minus j minus 1, right? So we know that I minus j is greater than 1. That means I minus j minus 1 is greater than or equal to 1, right? Now remember that sequence we started with? A to the first, a squared, a cubed, and so on. A to some basically positive integer. Well, I minus j minus 1 is one of these integers, right? This was all assumed to be in H, right, based on closure. And so that means that the inverse is in H. Right, so the inverse is in H. Okay, and so what we've shown here is that the inverse is in H whenever A is in H. Right, and that fact can be plugged into the previous theorem, the two-step test, and that shows that's everything we need, right? So if we have closure, then we automatically get closed under inverses, and that means we get the two-step test, which we got through the one-step test. Okay, and so these things are all daisy-chained, right? So as long as you can show that a group is closed, you automatically are showing that it's closed under inverses, and from that point forward, you've got that it's a subgroup, assuming the group is finite. Assuming the group is finite. Okay, excellent, excellent. So a little bit of a tricky proof. It's got a bunch of nice moves in there. Very abstract algebra-y proof. Once you get a couple of those, you start to recognize them, like, oh, that's definitely a proof from abstract algebra. And that's one of those. Okay, let's take a look at some examples, and then we're going to talk about another collection of subgroups that are important. Actually, let's talk about the subgroups first. So one of the subgroups that's important to our will be important to our work, specifically when we start talking about cyclic subgroups, cyclic groups in the next section, is this guy. It's denoted like this. Okay, A with these kind of like vector braces or whatever you want to call these little guys on the side here. This subgroup is a to the n such that n is in Z. Right, so it's very similar to the sequence that we just looked at in the previous proof. Okay, so A is some group, then A raised to the nth power, where n is an integer, is the subgroup of interest. And we'll prove that this is a subgroup in a moment, right? But this is basically just equal to, so you'd have like a to the negative third power, a to the negative 2 power, a to the negative 1, a to the 0, a to the 1, a squared, a cubed. Right, this guy here is the identity in this subgroup. Okay, so let's prove that this is a subgroup. So theorem, let G be a group, and let A be any element in G. Then A, as we've just defined it, the subgroup, is a subgroup of G. Okay. We can prove this one really quickly using the previous theorems. Okay, so let's prove this. So A is obviously in this cyclic subgroup, right? So it's non-empty. Okay, so it's a non-empty subset. And so letting a to the m and a to the nth power be two elements in this subgroup, well, subset we'll let a to the m power and a to the n power be two elements in this subset. Then we know their product, a to the m, oh, sorry, hold on, I got ahead of myself. Then a to the n minus m is also an element in this subset, right? It's just another integer. N minus m is just another integer. So this is just another element in the subset. Remember, this subset is a raised to an integer power, basically. So if a to the m, a to the n, they're obviously in this subset. A to the n minus m is another integer. A to some integer, that's in that subset. Okay. And what is a to the n minus m? Well, it's equal to a to the n times a to the m, the negative 1 power, right? So that means that is in the subset as well. Okay, and what is this? Well, this is just the old familiar AB inverse. Right, so your A is a to the n, your B is a to the m, B inverse therefore is a to the m inverse. And so that there is enough given the one-step subgroup test. Right? So a to the m, a to the n in A implies that a to the n, a to the m inverse is in A, which implies A is a subgroup of G. Okay, and so that would be the proof of that theorem. So any time you have this subset, it's automatically a subgroup, right? This is just exponentiating, right? And now let's take a look at an example of this. A couple of examples. These are interesting. Actually, I think I might have said it just now, but this subgroup just rewrite it one more time. The subgroup is called the cyclic subgroup of G generated by A. The cyclic subgroup of G generated by A. So it's a subgroup that's generated by a single element in the group. Okay. Now, sometimes A will equal G. Sometimes the whole group can be generated by this thing. And in that case, we say that G is cyclic. When this is true, we say G is a cyclic group. And we'll talk about that in the next section a lot. Okay. And in this case, when G is a cyclic group and A is what sort of generates G, we call A the generator. It's the generator of G. Okay, so just a little bit of terminology. We'll use some of this in the next lecture in particular. Let's do an example. Let's look at an example. Okay, so let's reuse our U10. So consider U10. Remember, that was the elements 1, 3, 7, 9. Now, it may not be obvious, but it turns out that 3 is a generator of this group. It's a generator of U10, right? And what that means is that the entirety of the group can be expressed as powers of 3. In this case, is a multiplicative group, right? So let's think about that. So 3 to the first power is 3, right? So that gets you that one. We already had it, kind of. 3 squared gets you 9, so that gets you that one. 3 to the third power is 27, right? 3 times 3 is 9, times 3 is 27, which is congruent with 7, right? And of course mod 10, right? So keep in mind we're mod 10 here. So that gets you that one. 3 to the fourth power is 81, and that's congruent with 1 mod 10. And so that gets you that one. Now you'll see that if you keep going, it just keeps kind of repeating itself. So 3 to the fifth power, you can think of that one. You can take shortcuts like this. So 3 to the fifth is really 3 to the fourth times 3 to the first. And 3 to the fourth is 1. 3 to the first is 3. And so that gets you the 3 again. 3 to the sixth is equal to 3 to the fourth, 3 squared. And so that's 1 and 9. So that gets you that one. So you see we're repeating ourselves here, aren't we? The next one would be 3 to the seventh, which is 3 to the fourth, 3 cubed, which is 1, and then 3 cubed is 7. Right, and so on. Right, 3 to the eighth equals 3 to the fourth, which is 1 and 1, which is 1. Right, and you could keep going, and you'll see that it just goes 3, 9, 7, 1, 3, 9, 7, 1, and then the next round would go 3, 9, 7, 1, 3, 9, 7, 1. It just keeps going. And so that's hence the name cyclic group. So 3 is a generator of U10, and so U10 is a cyclic group. It's a cyclic group. All right. Very good. Let's take a look at another example. And this one we'll say is, let's look at Z10. All right, so these are the integers mod 10. Okay, And let's look at 2, the generator here. Now, what you'll end up seeing, and I'll just tell you, but you can crank this out and see for yourself. This subgroup is 2, 4, 6, 8, and 0. All right, now this is an additive group, right? So keep in mind that this is an additive group. So we use n times a instead of a to the n. Okay, so just keep that in mind. But let's see what happens here. We can see how 2 will generate this. So 1 times 2 is 2. 2 times 2 is 4. 3 times 2 is 6. 4 times 2 is 8. And 5 times 2 is 10, which is 0. Okay, and now it starts to repeat itself. 6 times 2 is 12, which is 2. 7 times 2 is 14, which is 4. 8 times 2 is 16, which is 6, etc. Okay. So 2 doesn't generate all of Z10, right? We're missing in particular 1, 3, 5, 7, and 9, but it is a cyclic subgroup of Z10. Okay, so 2 is a cyclic subgroup of Z10. It is a better way to say it would be to say it is the cyclic subgroup of Z10 generated by 2. Okay. All right. Now here's another example, one that maybe would be surprising. We can actually what is a generator? What is a generator of so the integers under addition. We know that's a group. Identity is 0. It turns out that one number is a generator of this group. Okay, and the number is -1. That's interesting. Right, so you get the identity. All right, it's just 0 times -1 is 0. You get all the positives, all the positive integers by using the negatives. So -1 times -1 is 1. -2 times -1 is 2. -3 times -1 is 3, so on. And you get all the negatives as well. And that's just going to be 1 times -1 is -1. 2 times -1 is -2. 3 times -1 is -3, and so on. Right, so this element, the element -1, is a generator of Z plus. Cool. Okay. Very good. All right, let's talk next about what's called the center of a group. This is a very important subgroup. It'll come up a lot as we get further into the course. And so let's define it. The center, and it's denoted ZG. Okay, the center of a group G is the subset of elements in G that commute with every element in G. Okay, and so we could state it more concisely as ZG is equal to all of the A in G, all of the elements in G, such that A times X is equal to X times A, and that's for all X in G. Right, now we saw that in a commutative group, all elements commute with all other elements. In a non-abelian group, there's going to be some elements that don't commute with other elements. But there's always going to be some elements in the group that commute, right? And there's always going to be some elements in the group that commute with every other element in the group. Particularly the identity is going to commute with everything, right? But there may be others besides the identity. And when there are others besides the identity, other elements that commute with everything in the group, we call that collection the center of the group. Okay, so we call the collection of elements that commutes with everything the center of the group. Okay, and it turns out that the center of the group is a subgroup. So the center of G is a subgroup of G. Proof. Okay, so for this one we're gonna use a two-step test. We're gonna show closure, and we're gonna show closure under inverses. Just turns out that in this case, I think that might be the easiest way. There's different ways to prove it. We have a whole host of tests we could use. Right, so we'll start by showing closure. I.e., we'll show that the center is closed. So let's let E be in the center, right? Well, we're not letting it be in the center. We know that it's in the center because the identity commutes with everything. Every group has a center that is at least the trivial subgroup E. So E is in ZG, so that means that the center is not empty. Okay, and so let's show closure, right? Let's let AB be in the center. And so this actually is an extremely easy thing to show. Let's let X just be any other element in G. And so what we can say is then that AB times X is equal to A times BX, which is equal to A times XB. Right, now how does that work? Well, because B is in the center, so B commutes with X for sure. Okay, and so that's equal to AX times B. And now we can do the same trick with the A and the X. They commute because A is in the center. Okay, and so what we've shown then is that AB times X equals X times AB. So if A and B are in the center, then the product AB is in the center as well. Okay, so that means AB is in the center. Okay, so we have closure. Okay, so the first thing we wanted to show was that the center is closed. Now, secondly, we need to show that if we have an element in the center, then we automatically have its inverse in the center. So we want to show closure under inverses. Okay. All right. So we'll let A be an element of the center. And that means that AX equals XA for all X in G. Okay. So now we can quickly derive this. AX equals XA. Let's multiply both sides by the inverses. So let's bring the inverse into play here. A inverse times AX times A inverse equals A inverse times XA times A inverse. Okay. All right, now we've got a group, so associativity is fine, and so we can reassociate like this. And then you know what's coming. EXA inverse equals A inverse XE. So XA inverse equals A inverse X. And that implies that the inverse is in the center. All right. So if the inverse is in the center, then we're done. We've got closure, and we've got closure under inverses. This is exactly what we needed. All right. All right, so that's what we mean by the center. Okay, so the center of a group is the set of all elements in the group that commute with every element in the group. Okay, so the identity is sort of the trivial example of the center, but in some groups the center could be larger. You might have 3 or 4 elements in the center. You might have a dozen elements in the center, whatever. So a similar idea is what's called the centralizer. All right, so although an element from a non-abelian group may not commute with every element of the group, there are usually some elements that it does commute with. Right, so an element A and G may not commute with every X and G, but there are usually some that it does work with. That it I should use the word commute with. Right, and this is the idea behind the centralizer. Okay, so let's define it. We're going to let A be a fixed element in a group G. Let A be a fixed element in a group G. The centralizer of A and G, okay, and it's denoted, instead of ZA, it's CA. I'll denote it with that, is the set of all elements in G It's a set of all elements in G that commute with A, that do commute with A. Okay, so it's A is not in the center of G, but it is in the center of the centralizer of A in G. Okay, so some of these can be a little tricky. Let's write it out. I think it's actually easier to look at this stuff and notate in this kind of more formal notation. So the centralizer of A is all of the elements G in the group such that G of A equals A of G. Okay, so it's the set of all elements in the group that commute with A. Right, and so every element in the group is going to have some centralizer. Now, trivially, the centralizer will include the identity. It'll include A and the identity, right? But there may be others. Okay, we'll see that a lot of structure spins up off of these ideas of the center and the centralizers, etc. Let's see an example. I have one example to show. And this is from the dihedral group that we looked at on day 1 of group theory. And so let's consider D8. And I'll just rewrite this. Remember, we had the 0-degree rotation, the 90-degree rotation, the 180, and the 270. And then we had the horizontal, the vertical, and the 2 diagonal flips. If you go back and look at that first group theory lecture where we looked at the dihedral groups and symmetries of the square, this is the group we looked at. So these will look familiar if you've seen that, if you've worked through that. Otherwise, you're not going to have any idea what I'm talking about with this one. Now, all of these groups are going to have, this is not an abelian group. We saw that not everything commutes, right? But this is a group that has, there is a center and there are centralizers. And so let's look at a couple of these. So the centralizer of the 90-degree rotation, for example, it turns out that that's equal to obviously R0, which was the identity element. Obviously R90 is included in that, and it turns out that the other rotations are included as well. And that might be intuitive. I think it's intuitive, right, that rotation, 90-degree rotation, should commute with any other rotation, right? It doesn't matter if you first rotate 90 degrees and then 180 degrees, or if you rotate 180 degrees first and then 90 degrees. You're going to get the same answer, aren't you? Especially if it's all one direction of rotation. It's all counterclockwise rotation. All right, so this is the centralizer of R90. Now notice what's not in here, the flips, right? A 90-degree flip and a horizontal flip, right? So R90 and then a horizontal followed by an R90 is not equal to R90 followed by a horizontal, right? They don't commute. Right? So that for that reason, H is not in C90. CR90, sorry. It's not in the centralizer of the 90-degree rotation. Now it turns out that R270 has the same centralizer. All right, so this is also equal to the centralizer of R270. All right, so these two have the same centralizer. Now R0 and R180 are actually different. R0, the centralizer of that, is the whole set. Right? Everything commutes with this guy. Everything commutes with R0. R0 is the identity, so that makes sense. But it actually turns out that R180 commutes with everything as well. So the centralizer of the 180-degree rotation also commutes with every element, also includes every element in D8. Okay. Now what I would do, I would recommend people go back and look at this, because this is interesting. This is an interesting example. If you go back to that day one lecture, we actually built out an entire operation table, and you should have that in your notes. Just go back and confirm that this is true, like that these two rotations commute with everything, but the 90 and the 270 commute only with the rotations and none of the flips. You can go back and see that, and I think if you look at an actual square and you see like, okay, what's a 90-degree rotation do? What does the 180 and the R0 do? You'll see why all those flips get included in the centralizer here, but they're not in this one centralizer. Okay. All right. Very good. And I'm gonna state without proof that the centralizers are all subgroups as well. So for all A in a group G, the centralizer of A is a subgroup of G. Okay, so the centralizer is always a subgroup. Okay, so we'll leave it there. And this is one I think you could prove. You could use, I would probably use the one-step test on this. That's where I'd start. I have not done a proof for this one. I haven't proved this one, but this is one you could do. Very good. All right, so we'll leave it there, and the next lecture we're going to get into, we're going to kind of continue on this trajectory here. We introduced a lot of the mechanics and introduced the idea of cyclic groups, and so that's going to be the topic that we delve into deeply in the next section. We'll look at cyclic groups, a bunch of beautiful theorems related to cyclic groups, and we'll start to see what the structures of some of those look like. All right, we'll leave it there, and we will talk to you all next time. Take care.